Hi guys, so these are some practice questions that I didn't end up doing in the review session because students didn't have questions on them, but I thought I'd make a video for anyone else that is just going to hit on some of the main concepts with relative rate laws, regular rate law, integrated rate law, and like a quick little potential energy diagram review. So what I would say is pause the video on a question, try it out, and then check your answer with mine. Also, I'm answering these as I go, so if you see an error, you just got to let me know. All right, so this first one is a relative rate law, and how I can tell is it's giving me a reaction. It's talking about how one reactant or product is increasing or decreasing at a certain rate, and then it's asking about the rate of a different reactant or product. So with this, I can see that H2 is one of my products here. So it's talking about it's increasing, so it's getting produced at this rate of 0.030 molar per second, and it wants to know about NH3. So because of these in terms of for every 3 molecules or 3 moles of H2 getting produced, it's going to be consuming 2 moles or 2 molecules of NH3. So I can use that relationship in the stoichiometry between them to find the rate that NH3 is going to be disappearing. So I'm going to start with my mole of H2. So I'm just starting with the rate. And just to help with the conversion, I'm just writing it out like this, same thing with my units here. And then I'm just going to use my mole to mole conversion. So for every 3 mole of H2 produced, it's going to consume 2 moles of NH3. So 0.03 times 2 divided by 3 is going to get me 0.020, keeping the 2 sig figs that I started with. And now this would be in mole per liter second in terms of my NH3. So this one is the rate, and we express rates as positive numbers, but when we talk about it in the end in terms of a reactant that's getting consumed, we would say then that this would be negative. So you may see a negative there to show the fact that it's disappearing. Okay, and that's all it is. It's just a mole to mole conversion. I think is the easiest way to take a look at it. And this is just like our relative rate change. Okay. All right, let's take a look at the second question I have. So again, if you want to pause it, this is asking you to determine the rate law and then determine the rate constant. And of course, make sure you're including units here. All right, so if I am taking a look at these two, okay, I'm going to be looking at where one is held constant versus the other one. So just because it's jumping out to me initially, I'm going to be looking at the concentration of B just first. I can see that in trial 2 and 4, it's constant. So if I look at B doubling, okay, I can see that nothing is happening to the rate. Okay, nothing happens. Okay, because of that, I then know that for B is going to be 0 order, where if I change the concentration, nothing happens to the rate. That means it has no effect on the rate of the reaction, so it's going to be 0 order there. All right, if I take a look at, and I'm trying to look for numbers that are easy to like analyze. So if I take a look at, let me just try this one out. So say I have 1.125 goes to 0.375, and I'm going to look at the rate there. So 125 raised to the second would be, that's not what I wanted. 125 times 2 would be 0.25. So I am multiplying this by 3 when I go across from there. So this is changing by like a power of 3, or not a power of 3, I shouldn't say that. But I'm multiplying it by 3, and when I look at the rate, the 7.25 times 3, I get the same thing. So they're changing by the same factor. Even though I wasn't talking about doubling it, I'm talking about really tripling the concentration. The same thing follows with the rate, where I'm tripling the rate. So because those are a direct relationship, I then know that for A, that's going to be first order. Okay. Say you couldn't see that, or you were having trouble analyzing the data. Remember that you can write it out. So say, I'll show you one example of this. I would have my rate of 2 over my rate of 1. And then remember, this would be K, and then you have A to M, B to N, and this would be all for the second trial. And then this would be 1. And again, this would just be a way of just like verifying your data if you really weren't confident in your answer. So remember, the rate constant is going to be the same for each of these. The concentration of B stays the same. So I'm just using the concentrations of A and then my rates for those two. So my rate of number 2 was 21.75 molar per minute over 7.25 molar per minute. Okay, my concentration of A for the second trial was 0.375, and this was 0.125 raised to M, so 21.75, 7.25, oops, we give you 3, 0.375 divided by 0.125 would also give you 3 to the M. So in that case, M would have to equal, 1. So it's another way you could do it if you just didn't see how the numbers were working out. So anyways, that allows us to get the rate law. So remember, the generic rate law is rate, K, and then we're just using the letters that they used for our two reactants. Okay, we found from the table that A was first order and that B was 0 order, which means that it ends up getting removed from the rate law. It won't show up. Okay, so this would be my final answer based on our experimental data. Now, to find the rate constant for this, you can pick any trial. I just always go with the first one. It's just out of habit. So I'm just going to be taking the rate and my concentration of A to find my rate constant. So my rate here is 7.25 mole per liter minute is equal to my unknown rate constant, and then my concentration of A in that trial was 0.125 mole liter. Okay, when I then rearrange it, I would have my 7.25 mole per liter minute, and then 0.125 mole per liter. Okay, so if I do 7.25 divided by 0.125, I get my value of 58, which based on my 3 sig figs for both of those, I'm going to make it 58.0. And then for my units, you could do this 2 ways. You could just take the units that are shown, and if we rearrange this, it'd be mole liters times minute. And then if I flip the units here, so that instead of dividing by moles per liter, I'm going to multiply by liters per mole. Okay, that would allow me to see that I'm just going to have 1 over minute. Okay, the other way to do it, remember, is if you look at the generic per time, okay, I would just be plugging in, this would be my overall order of reaction is 1. So this would be 1 minus 1, 1 minus 1, which would give you 0. Okay, which just eliminates the liters and moles, so that would also give you 1 over time. So either way, you're going to end up getting to 1 over minute. Okay, so that would be what K should be equal to there. Okay, so that kind of walks you through an example of like a rate law, how you can analyze the table, how you could do it in the algebraic method, and then a little bit quick thing about units, which if you really struggle with units in the review session that you can email me about, you can ask me for the video of that, and it gives you a good review of units. Okay, all right, moving on to the next question. So again, read it, pause it, and then you can jump back over with me. So this is talking about ammonium cyanate reacts to form urea. At the given temperature, it gives you this rate constant, and it says, what's the rate law for this reaction? So one big thing with this is K should obviously be in our equation here for this reaction. So C and D are like out of there right off the bat. The other thing is we can get rid of E because we have a product here in the rate law expression, and our rate laws need to be expressed in terms of our reactants. So this one's out. So I'm really just narrowing it down between these two. A is representing a first order, B is representing a second order. If I take a look at my units, and again, this is where units come in and are really helpful, that unit is for a second order, okay, which means we got to have second order in terms of our rate law expression. So that means B is going to be my answer there. I can quickly show you from the review session. This was kind of like what I walked students through. I started with the generic formula, and I just worked through like how 0 order gets us to moles per liters time. how first order gets us to 1 over time, and how second order, just like in this example, gets us to liters over moles time. Okay, so that can be really helpful in terms of helping us identify what should be the overall order of reaction. All right, let's try it out and look at number 4, which is now going to move into integrated rate law. So again, I would suggest pausing this, trying it out on your own, and then checking back in with me. So this is telling us about how we have a painkiller that has a rate constant, or the active ingredient has a rate constant of this value, okay, which I can tell right off the bat based on the unit, which is 1 over day, that this has to be first order. Okay, again, just based on this little chart I gave you, here's my generic unit template, and then it's going to be first order when it's 1 over time. So it says that allows me to know which equation I'm going to use. So how many days does it take for 15% of the original ingredient to decompose? So I'm going to first just set up my formula for first order, and this would be right off your AP reference tables. Make sure you always check it, especially to make sure that you're either putting the negative in front of the KT, like in 0 in first, or not for second. So this is just talking about 15%. How I would choose to do this would be just to start off with a 1 molar value here. So I'm going to have the Ln, and I'm going to pick it as 1 molar. I'm going to fill in my 9.05 times 10 to my -4th 1 over day, and then I'm going to be looking for time. So what do we need to put here for our final concentration? Well, if I have 1.0 molar and 15% of it decomposes, that means I should have 85% left. So 85% of that 1 molar would be 0.85 molar. So 85 decomposes, gets consumed, or decomposes, reacts. So I would have a concentration 0.85 left, okay, or 85% that still remains. So that's the number that I have to make sure I put in here. So just be really careful with these types of questions that you're figuring out this final value correctly. And there's other ways you could do this too. This is just how I kind of go through it, starting with the 1 molar. So this would be 0.85 m. All right, so if I go and plug this in, okay, I'm going to have my Ln of 0.85 minus my Ln of 1. Okay, I'm then going to divide. I'm just going to leave this running in my calculator. Divide by -9.05 times 10 to the -4th. Okay, and then this would give me, and I'm going to just, I'm going to use the rate constant in this case, so 3 sig figs. So I'm going to round that to 180 with a decimal days would equal time here. Okay, so I picked this one because it's a little bit, 2 things. One, you had to use the rate constant to figure out the equation. So be really careful with those units. And then just this little extra part, again, about understanding when it talks about 15% decomposing or reacting, and then how you would come up with this amount that's still in solution. So just make sure this value here has to be what remains in solution. Okay. All right, let's look at a second order rate law here. So here I have butadiene. It's reacting with, looks like octane there, and it gives us this rate law. So this is giving us a couple things. It's giving us the rate law, and it's giving us the rate constant, which match here. Here's units for second order. It's also showing us that this is second order. And why that's important, it's going to tell us what formula to use. So remember, integrated rate law, you're going to know that you need to do an integrated rate law because this is talking about time and changes in concentration, okay, which is essentially what we're doing when we're doing our integrated rate law calculations. So with this one, I'm going to have the reciprocal. So this is 1 over my final concentration minus 1 over my initial concentration. And then this is positive KT. Okay, so I'm looking for 1 over my final concentration, and I'm starting with 0.025 m. My rate constant was 0.014 liters per mole second. Now, as soon as I write that second, I realize my 3 hours need to match that unit. So I'm going to take my 3 hours and I'm gonna make sure I change it to seconds. So in every 1 hour, I get 60 minutes. In 1 minute, I get 60 seconds. So 3 times 60 times 60 is gonna give me 10800 seconds. Okay, I'm gonna leave it like that. We probably should technically round it to the 2 sig figs there, so I guess we should do that. I'm gonna cross this out and this would be 11,000. Okay, just to keep my 2 sig figs. All right, so from here, I am going to, how I would go about doing this is I'm gonna multiply my left-hand side. Okay, and then I'm going to add this value here. So I get this value. I'm not going to worry about rounding off right now. Equals 194. And then this is just how I have to mathematically go through this. So this I would cross multiply, which then when I do 1 divided by 194, I get 0.005. And going back to my original 2 sig figs, I'm going to get this. So this is what I got in my calculator. Molar. That would be my final concentration at time t. Okay, so this would be my answer here. All right, so that's just an example of second order. We had to keep track of, first off, identify that it's second order, get our right equation. And then the only real tricky part with this one was, again, just making sure the units of time match up with our rate constant. And then just working through the steps here. Okay, so that was an example of a second order question. And then the last one I have is just a quick little potential energy diagram in case you had trouble with the example in the bell ringer. So this is talking about, it has an activation energy of 102 kilojoules per mole. It gives us our delta H and it wants to know the activation energy for the reverse reaction. So I'm just going to kind of sketch out, okay, the information that I know. So one little thing is I can tell from this positive that this is endothermic. Okay, so what that means is I know then it's going to have, where my products have to have more energy than my reactants. So that's the little part that's telling me that piece of it. So I'm going to have my reactants and then my products here. So I know that this value is going to be 55 kilojoules per mole. I know that my forward activation energy would be represented by this bar here, which would be 102. Okay, so if we're looking for the reverse activation energy, this value here, you can see how these end up lining up with each other. Okay, where this reverse activation energy, so EA of the reverse, would just simply then be 102 minus 55. Really plug that in. End up with a value of 47 kilojoules per mole. Okay, so that's just another little one of you had trouble on the bell ringer. All right, that is it, at least for these just initial basic just review questions in case you needed a little help from all the stuff we've covered this week.